All right, let's do some quick questions involving permutations and factorials. Okay, question 1. You have 22 people in the class. We need to elect a president, a vice president, and a secretary. How many arrangements are possible? Okay, so in this example, we have 22 people. That's our n number. And we have 3 positions here. So we can think of this as 22p and 3. And that will be our result. Notice that this would also be equal to, if we did this, 22. Once we picked the president, which was 22 options, we would now pick the vice president, which would be 21 options. And then we pick the secretary, which is 20 options. Notice this is all equal to 22 factorial over 19 factorial, which is the definition of 22p3. So these two ideas are consistent whether we draw this way or we state it this way. These are both good answers. Okay, 5 people stand in line for a photo. How many arrangements are possible? Let's go with 5, and we're choosing all 5 of them, so it would be 5p5. Or we could simply say, hey, that's 5 factorial. Now something we could argue is it different? Is it a different order if it's the order of 1, 2, 3, 4, 5 or 5, 4, 3, 2, 1? Well, we'll leave that up in the air. So if we're going to say those are different, then we would divide those options all by 2. But let's just say that's not different for this question. A family with 4 children stand in a row. How many arrangements are there that do not have them in order of birth? Okay, so again, it's 4 people, and we're picking all 4 of them. So that's just 4 factorial, right? So either one of those answers would work. However, what we're trying to do is avoid having them in order of birth. So I would argue on this one, if we had them in order of 1, 2, 3, 4, so oldest, second oldest, third oldest, youngest, or we have 4, 3, 2, 1, either one of those is actually the order of birth. So there'd be 2 options in here that would leave them in the order of birth, which is 4 factorial then, and we minus 2 options off of that. Okay, we have 10 people sitting around a rectangular table. 1 person at each end. How many arrangements are possible? So let's get a little picture of this. We have a table, we have a person on this end, a person on that end. 1, 2, 3, 4 on this side. 1, 2, 3, 4. And this is just a beautiful family gathering here. Large family gathering. All right, so 10 people sitting around. So it seems like it would just be 10 factorial. Now, I would argue to you that there's kind of 2 unique spots here. This is a head and this is a head of a table. And if we want to see either of those as heads, then we could think that if we had the order as 1, 2, 3, 4, 5, 6, 7, 8, and let's call this H1 and H2. And if we took this whole table and rotated everybody around a full 180 degrees, so H2 becomes H1 and H1 becomes H2, and 1 would become 5 and 5 would become 1, what you'd end up with is the exact same arrangement. There would be no difference. So because of symmetry, what we're going to do is we're going to divide it by 2 because, well, it'd just be the same picture if we rotated everybody else around. I'm going to dig a little bit deeper into this symmetry thing. Okay, what about if you have 10 people sitting around a circular table? How many arrangements are possible? So again, you have a circular table and you have all these people. I'm not going to make a good guess on this, on 10 arranged nicely, but again, you'd have 10 factorial ways of arranging them around a circular table. This time, how many times would there be exact rotational symmetry? So if we think of this as position 1 here, and this is position 2 and 3, and this is position 10 right there, if everybody just picked up and moved one clockwise position, so everybody moves 1 this way, including the other 4 through 9 people, it would be the exact same picture. So somehow we need to take care of this fact that it would rotate and everybody would be the exact same. So this time there are 10 rotational symmetry. Okay. So the answer is 10 factorial over 10, or 10 factorial over 10 is just equal to 9 factorial. All right, what if you have 8 people sitting around a square table? How many arrangements are possible? Again, 8 factorial. Think about a square. Picture a square in your head. You'd have 2 people on all sides of this table, right? Well, how many times would you have a perfect rotational symmetry? There would be 4, because it's a square. There's 4 rotational symmetries. Okay, what if you have 9 people around a triangular table? You know this is a math question when we set up a triangular table. All right, how many times would you have rotational symmetry? Again, 9 factorial over 3 this time, because there's 3 times it would be rotational symmetry. Now you do have to buy in with me on some of this. I'll back up to the previous question. So if I number those people 1 through 8, if everybody moves 1 position to the right, so 1 becomes 2 and 2 becomes 3, let me just draw that for a second. So here's 1, 2, 3, this would become 8. If I just look at it from the perspective of 1, okay, so 1 right here has 2 on its left, and 8 is not quite on its right. It's kind of facing on a perpendicular angle, right? And here 1 is actually sharing a side with 8, and now is perpendicular to 2. So I would say that these two things are different. Whereas if 1 went to position 3 and everybody moved 2 over, then again it would be beside 2 but perpendicular to 8. All right, these are your quick questions on permutation and factorial questions.